Okay. Yep. Okay.
Thank you for coming, everybody. So this is a joint work with Sasha Barak, that probably all of you know. And people ask me to give a detailed example of this construction, so I will try to give that. And if I have some time, I will talk also about some extensions. Okay, so we dive into the repair problem to understand what we're trying actually to solve. So we try to understand it through Reed-Solomon codes and understand what are their limitations. So if we look at 1410 Reed-Solomon code, as far as I know, this is what is being used in Facebook. So they take chunks of data, they generate extra 4, and you're immune to any 4 failures. But what happens if you lose one? You start to repair the lost chunk, and we know that you can do it only by accessing 10 other chunks, not less than that. So it requires 10 times more reads compared to the amounts of data that you actually want to repair. You read 10 symbols, you actually want to recover 1. And then if a large portion of the cluster is Solomon coded, it will saturate your network. So that's the problem. Okay, so people came up with the notion of locally recoverable codes. And what is NKR LRC is the following. It's a code of dimension k. It takes n k blocks, generate n blocks. So if you add extra n minus k. And what is this k r parameter? It says any block has a recovering set of r other blocks. What does it mean? You lose block number 2. There exists some r other blocks such that if I read their value, I can recover symbol number 2. So it's the first observation that r is between 1 and k. Why is that? You have to read something in order to recover your symbol, so it's at least 1. Why is it at most k? Because I can read k other symbols, decode the entire code word, and then I can recover also my lost symbol. Okay, so the first question to answer, what is the connection between the locality and minimum distance? So this answer was actually answered, this question was answered by these guys at Microsoft Research. They actually defined this notion of LRC, and they gave this bound, the d is at most this number. And the first observation is, the smaller the locality is, you have to pay. If you want small locality, you have to pay by failure resilience. If you're this r, you have to pay somehow. Another observation that this is a generalization of the singleton bound. If you plug in r equals to k, you get back the singleton bound. And this is, in fact, actually a bound that incorporates also the locality of the code. And we say that the code is LRC is optimal if it achieves the bound with equality as the best possible distance. Okay, so what are the previous constructions? So the first construction in 2012 by Vijay and his students, they gave a construction with the following parameters. The downside of the construction is the restricted length. The length of the code, is a function of r and k. But the good side is the field size. The good side is the field. So the field size is more or less n. And then in 2013, there were 3 constructions. So these are guys in UT Austin, and then Microsoft Research. Downside, the field size is very large, it's exponential. But the parameters are very flexible, almost any n, k, and r. So the question is, can we combine these two, have small field size and also a flexible set of parameters? So let's look at the easy cases and see if we can solve this problem for the easy case. So this is the bound that we know. And if we plug in r equals to k, as I said, we get back the singleton bound. The question, can we construct such an optimal code that it shifts this bound with equality and has locality k? So indeed, we can construct a Reed-Solomon code as a locality k, the worst possible locality, but it also achieves this bound with equality as the best distance. And the field size is order of n. Now let's look at the other extreme case when r equals to 1. If you plug in r equals to 1, you get the following bound. And then you ask yourself, can I get an optimal code that has locality 1 and achieves this bound with equality? So the answer is indeed yes. What do? You take n over 2 comma k Reed-Solomon code. You get n over 2 symbols, and you just replicate each symbol. So in total, you have n symbols. Each symbol has its twin symbols, so you have locality 1, and the distance of the code is twice the distance of the original code, and this is the distance of the original code, so you get twice the distance. So again, we can construct for this extreme case, for r equals to 1, we can construct a code of field size linear in n. So the question is, what happens in the middle? Can we construct codes when r is between 1 and k? So what is the properties of our construction? It's optimal distance, flexible set of parameters. The field size is comparable to the code's length. And it's a natural generalization of the well-known Reed-Solomon code. The reason I put it in red is because Reed-Solomon codes are widely used in theory and in practice, and we can actually use known results about Reed-Solomon codes and their generalization in our construction. I will talk about it later. Okay. So what is the intuition behind the LRC construction? So if we take a Reed-Solomon code, information vector is actually defined to as a polynomial. What we usually do, we can draw the graph of the polynomial, and we evaluate the polynomial at certain points, endpoints, and we get the evaluation vector, and this is what we store. We forget about the polynomial, and we store these dots. Now, if I lose one symbol, what do? I recall that actually this evaluation came from evaluating a polynomial of degree at most 3. Therefore, it is enough to read 4 other symbols and recover the polynomial. And after I recover the polynomial, I can recover the lost symbol. This is how we do decoding, local decoding, or in fact decoding for Reed-Solomon code. The problem is how much we pay. We need to read 4 symbols, and this is in this case, this is the dimension of the code, which is not good for us. It's too high. So how can we reduce the locality? Oh, so after we decode, we get back the symbol. So how can we reduce the locality? If a genie came to us and told us that through our point that we are looking to recover its value passes a low-degree polynomial through our point and through enough points that we already evaluated that. So that now we're back in business, because now it suffices only not to reconstruct the original polynomial, but to reconstruct the low-degree polynomial. So in this case, the low-degree polynomial is just a linear polynomial. So if we read these 2 values, we can reconstruct the line, and then after we reconstructing the line, we can recover the lost point. So the idea is just to make sure that all the time, through any points that we evaluate at, there exists a low-degree polynomial that passes through this point and through other points that are already evaluated at. So what is the construction? So what are the ingredients? So we start with A1 till AN over R plus 1, disjoint subsets of the field F, where the size of each subset is R plus 1. So you have, in total, n points of the field. What is the second ingredient? G is a polynomial in the ring of polynomials over that field. And what are the constraints from G? What do we want from G? G is a polynomial of degree R plus 1. And we want G to be constant on each subset AI. So if I evaluate G at the point alpha and the point beta, where alpha and beta are in the same set, AI, so I want G to be constant on it. Assuming that I found this set of subsets and this polynomial, I can construct a code. How do I construct a code? So I take k information symbols aij, where so I have 2 indices for the information. I goes from 0 to r minus 1. J goes in this is in this set. And I define the following polynomial. I goes from 0 to x to r minus 1, x to the I, and then I have a second term. And there is a reason why I drew it in green. I painted in green. So this is the encoding polynomial. And after I define the polynomial, I evaluate that polynomial at the points alpha 1 to alpha n, where alpha I are in the subsets that I picked. So the claim is that this is an optimal LRC, optimal code. So a few remarks about the field size. So the only constraint about the field size, more or less, is just that we have enough elements in our finite field. So we need n distinct elements. So the field size has to be at least n. But this is more or less the only constraint. The second remark, if I put, if I assign here r equals to k, if you plug in r equals to k, j goes from 0 to 0. So basically what you end up with is a polynomial of degree at most k minus 1. What I'm saying is when r equals to k, this construction boils down to Reed-Solomon code. So as I promised, this is a generalization of Reed-Solomon code. So I want to show the optimality. So I'm claiming that this is an optimal code. So why is that? So first of all, about the distance. So if I calculate the degree of this polynomial f, the degree of this polynomial f is at most r minus 1 plus, this is the degree of x to the I, plus the degree of the inner polynomial. So the degree of g is r plus 1 times k over r minus 1. This is the highest degree of j here. So the degree of f is at most this number. If you open the brackets, you get this is equals to k plus k over r minus 2. You do the calculation. So our evaluating polynomial is degree at most that, so therefore it has at most this many roots. And since this is a linear coding, and the minimal weight equals minimal distance, so the distance is at least n minus k plus k over r minus 2. And if we go back to the singleton bound, we see that this is exactly the singleton bound. So I just proved to you that this code actually has best distance. The question is, why does it have this promised locality? So for that, I will define the following polynomial. So fi will be the green part. So j goes from 0 to k over r minus 1, aij, g to the j x. So after I define this polynomial, so the encoding polynomial becomes the summation I goes from 0 to r minus 1, fi of x, x to the I. So we call this polynomials fi, the coefficient polynomials, because they act as the coefficient to the term x to the I in the polynomial. So what can we say about this polynomial fi? We know that g is constant on the subsets. So also g squared is also a polynomial that is constant on the subsets. And actually any power of g is constant on the subsets ai. So if you take a linear combination of polynomials that are constant on subsets of ai, of the subset capital A, and you get also a polynomial that is constant on this subset. So basically what I'm saying that all the fi's are polynomials that are constant on the subsets fi. With this observation, we can actually prove the locality. So let's say that we want to recover a symbol that was belong to the set for alpha in the set A1. We want to recover f of alpha. This is what we want to recover. Where should I write it? Okay. So we define the following polynomial, delta of x equals the summation I goes from 0 to r minus 1, fi of a1, x to the I. So as I said, fi is constant on the set a1, so this notation makes sense. So you just check the value that fi gets on the subset a1. Now, if I go to here. So there is this very easy claim. The following claim is very easy to prove. What is this claim? So I'm saying for any alpha in the set, for any beta in the set A1, for any beta in the set A1, f of beta equals delta of beta. So this f is the encoding polynomial, and delta of beta is defined there. Why is it true? This is very easy. So what is f of beta? This one equals to the summation I goes from 0 to r minus 1, fi of beta to the I, but this equals to the summation of fi a1 beta to the I, because beta belongs to a1, and then this equals to delta of beta. Now, if I want to, so I want to know the value of f of alpha, since alpha is in a1, this one equals to delta of alpha. So actually I need to know, if I want to know this value, I need to actually evaluate delta at the point alpha. So if someone tells me what is delta, I'm done. Now delta is a polynomial of degree r minus 1. So I need to know only r points on delta, and therefore I will be able to know delta, and then after I know delta, I know the value of what I'm looking for. So what I'm doing is, so I'm reading the values, the following values. I'm reading f of beta, which equals delta of beta, where beta is in the set a of 1 minus alpha. So all these symbols are available to me. So this set, so I'm actually getting r evaluations of delta and r distinct points. So I can recover, once I'm reading f of beta, it's actually reading, I'm getting evaluation of delta at r distinct points, and therefore I can recover delta, and then I can recover my lost point. Questions? So let's look at an example. So let's say I'm trying to construct 942 LRC over F13. So I need 9 evaluation points. So I take the following sets: 1, 3, 9. Second set A2 is 2, 6, 5, and the third set is 4, 12, and 10. And my G will be x2, x cubed. So you can check, you can easily check that G is actually constant on each of these subsets. So if you plug it into the formula here, the encoding polynomial f of x equals a0 plus a1x plus a2x cubed plus a3x to the 4. As you can see, we are missing one monomial here. We don't have the x squared. So assuming that the information symbol is the all ones vector, so we plug it into we get the following polynomial. This is the polynomial that we're encoding at. And we encode at this 9 points, 1, 3, 9, 2, 6, 5, 4, 12, and 10. We get the following information vector. The following evaluation vector. And let's say we lose the vector, the point f at the point 1. What do we do? How do we do local recovery? So we know that this decoding polynomial delta is of degree at most r minus 1, where r equals to 2, so the degree is at most 1. And we need 2 extra points. So we read the value of f at the point 3, which equals delta at the point 3, which equals 8. And then we read another point, f at the point 9 equals delta at the point 9 equals to 7. We do this polynomial interpolation, we solve this equation, and we get delta equals 2x plus 2. We evaluate delta at the point 1, which equals f at the point 1, which equals 2. Okay, so If I want to compare this 942 LRC with the Reed-Solomon, 94 Reed-Solomon, so we get the following properties. So both codes can be defined over a field of size 13, even 9. The minimum distance for the Reed-Solomon code, of course, we cannot beat that. It's 6. It's best possible. But in here, we get slightly less, 5. But the gain is in the locality. Here, it's 4. And here, you reduce the locality by half to 2. OK, so
just going back there, you could have the 9.4 RS code over the size 9, right?
yes.
But
What?
But for this LRC, you have to have 13.
No.
You can also have for 9.
Yes. I can also have it for 9. OK. But you will have to. OK. You can also use for 9, but yeah. OK. So let's talk about the ingredients. So we assume that we can find these subsets and this polynomial g that is constant on the subset. The question is, how can we find them? So there is a very easy way to do it using the following claim. If H is a subgroup of the multiplicative group of the field or the additive group of the field, then the annihilator polynomial of H, which is defined like this, is constant on the cosets of the subgroup. So the coset of subgroup of the subgroup partition our space. So this gives us the subsets that we are looking for. So this is very easy to prove.
It's even 0 on the set, not only constant.
No, it's 0. It's on the subgroup, but it's constant, which is not 0 on the other cosets. So using this algebraic structure of the field, we can easily get these ingredients. And going back to your question, we can use subgroup F9. We could use subgroup of size 3 within the F9.
So a little thing. I understand everything, but there is. So you don't lose. So you can evaluate on every point on the for Reed-Solomon, you could evaluate on every point, but for LRCs, you have to leave out. You might have to leave out a little number of points, right?
No, what? No. If I use, for example, if I use a subgroup of the additive group, I can evaluate at all points of the field.
Yeah. Okay.
Okay. Let's talk about multiple recovering sets. So the next question is, okay, now I've shown you how to get one recovering set. Let's say you want several. So how do you do that? So there's a few ways. One way is to take product codes, but there's a different way, which gives you slightly better parameters, is the following. So our method constructs a subspace of polynomials that if you evaluate these polynomials at these sets of elements, you get some locality, R1. So this is a large subspace that we have constructed. But using the same method, you can also find another subspace that has locality R2. So if you look at the intersection, if you evaluate only at the polynomials that are in the intersection of these subspaces, you get both properties. You get polynomials that gives you locality R1 and also R2. And you can get several recovering sets this way. That's the idea. And I want to give an example and compare it to replication. So main advantage of replication is high availability for hot data. What is hot data? Data that's been accessed frequently. And we want to construct LRC with high availability with small overhead. How do we do it? So we give an example of codes of dimension 6. You add extra 6 symbols. You get in total 12 symbols. And you have each symbols among these 12 symbols as 2 recovering sets, these joint recovering sets, one of size 2 and one of size 3. So what is the encoding polynomial? This is the encoding polynomial. I wrote it just to show you that the structure of this polynomial, there are many monomers that are missing, and the structure is a little bit weird, but this is what comes out. Okay, so I want to compare this 12-6 LRC with the replication. So in replication, 3 times replication, it's widely used. So if you have 6 symbols, you replicate them 3 times, you get in total 18 symbols. And I wrote here 1 and 1 because each symbol has its 2 twin symbols, so its recovering sets are 2 disjoint recovering sets of size 1. So the overhead in the replication, 3 times the replication, is 200%. You add extra 12 symbols, in our construction, the gain is very clear. The overhead is only 100%. Let's look at the resiliency. So this code can tolerate any 2 disk failures, not more than that. And what's surprising that our code can tolerate even more than that, 3 disk failures. And if we look at the availability of the information, so here each symbols can be read simultaneously 3 times by 3 different users. And in our construction, you have the original symbol, and if this is being used by our user, you can go to the recovering set and recover this symbol. And if this is being used by our user, you can go and read the 3 other symbols, recover your symbol, and get your data. So this, in a way, mimics the high availability for raw data, but with a big gain with the overhead and the failure resiliency. Okay, how much time? I don't know. 4 minutes. Okay, so let's say we want to be a little bit more greedy, and we want to have much smaller field size compared to the length. So there are natural ways or extensions to do that. So we call this construction I just presented the read-someone type construction for LRC codes. So if we restrict the field size and we're trying to increase the length of the code, this naturally leads to AG codes. And another way to get small field size compared to the left is to restrict the left, construct the code using this construction, restrict the left, and then to look at subfield subcode. So you're just trying to decrease the field size. So this naturally leads to subfield subcode. So this is two extensions that we recently submitted to papers that we submitted to ISIT that goes along these 2 ways, two paths. So I want to talk about cyclic LRC and their subfield subcodes. So this is a joint work with Shri Goparaju and Rob Calderbank together with Sasha. So if we have a code that is LRC over FQ to the M over a large finite field, we can say something about its dual code. So we know that the dual code contains code word of weight R+1. This gives us the locality. Now, if we want to look at the restriction of the code to a smaller field and analyze the locality of this code, we need to look at the dual code of that code. So the connect relation between C dual and the C dual of the restriction is well-known result of Del Zart is using the trace mapping. So this is how we analyzed our codes using the trace mapping, and we can say something about the locality of this code. The locality of this code. Okay, so I want to just maybe end with a surprising observation. So when you construct a code and you look at the subfield subcode, this distance does not decrease. It many times actually increase if you look at the subfield subcode. And the same thing works here. What I'm saying is with the locality. So if you have a code C over a large finite field, and you restrict yourself to the smaller field, FQ, clearly you have the same locality. So you throw out vectors or code words, you didn't ruin the locality. So of course this code has locality R. But what is surprising is that in many times, the locality does not only it does not increase, in many cases it's much less. So this is for me in the beginning it was kind of surprising when I saw it. So I won't get into that, but I will just give an example. So this code, 4333 cyclic code, with this set of roots, the locality is 14, and the field is over. It is defined over the field 2 to the 12th. So the locality is 14, but if you restrict your code to F2, you get the following code with the same length and dimension, but the locality reduces by half, which is kind of surprising. And we can say more than just about the locality. We can say something, how many recovering set you have, and so on. And this comes into the picture. To analyze these codes and the restriction, we need to use some known results from irreducible cyclic codes.
Sorry, but if the distance doesn't suffer and the dimension doesn't go down, this means that the original code wasn't on this MDS type bound.
Yeah.
Has to go down, right?
But
No. Why? No. This is a complete. I just picked a complete cyclotomic. This is one cyclotomic coset, so the dimension does not go down.
right, so distance actually distance remains the same, but it's over binary.
Wait, so the original code should not have been on this MDS type bound, right?
No. I'm not saying that it was.
I mean, if it were on the bound, then you should suffer something. I mean,
Yeah. I'm not saying it was. It's not.
I think you lose on the dimension. When you go to the subfield.
No, but I specifically picked a complete. This is one complete cyclotomic coset. So you just take the closure of this cyclotomic coset. You just take this. You get the
It
same.
means the original code is just copies of a binary code with shifts, right? That's what it means. It's like the higher the field, it's just 12 copies of the same code shifted over.
Anyway, let's continue. I would just. How much time? Okay, I'll just end with this. I won't say much about that. This is a joint work also with Serge Vladuts. So we can generalize this construction similarly as Ritz-Solomon code can be generalized into GOPA code. This can be generalized to AG codes. And the local recovery is done through polynomial interpolation. And we can construct asymptotic good codes. That's it. That's what I want to say.
All right, maybe one question while Mary.
Actually, fight. I don't know. You claim. Yes, sir.
So what, doesn't any lower bounds for binary case are known?
So there is a bound. First of all, there is a bound on the distance that Arya gave. But you're talking about constructions, yes?
No, I'm talking about lower bounds. Like, do you know what kind? So, what is known about if you restrict yourself to binary case? What is known upper and lower bounds? What's the case?
So not much is known. So we have a paper about that.
There is an upper bound, and lower bound is something like LDBC codes. I mean, achievability is something like LDBC codes for the binary case.
And lower bounds.
Okay, so by lower bound you mean impossibility?
Impossibility.
Okay, so that's upper bound here because.
Yeah.
So there is a bound.
So this is exactly.
Pretty simple.
For regular code,
Right. So if you knew that exactly, you could compute it exactly as well. But you don't know that.
So Ilse, your construction, isn't it related to earlier construction of like redundant residue codes?
So you can view it as redundant residue codes. It's in fact you can view it as they took it off. I continue. Okay. So you can view it as we talked about it in the paper. You can view it as a Chinese reminder theorem. Yeah. Exactly that. Yeah. But there's some added. You need to pick the points that you're actually evaluating at. But yes. No more questions. Okay. Thank you.